All right, let's dive right into this explainer. Today, we're looking at the absolute bleeding edge of automotive engineering. We're going to break down exactly how engineers prevent catastrophic failures in electric vehicle batteries. Specifically, we're looking at the battery management system, the BMS, and what actually happens when the memory inside its brain starts to fail. Now, this is a pretty highly technical breakdown, but I promise you, by the end of this, you are going to look at an EV in a completely different way.
So what happens when an EV battery's brain suddenly just goes blind? In the engineering world, we're talking about specific diagnostic trouble codes, things like P0A1F, P0A0F, and P0A0E. These codes essentially mean the BMS has suffered a hardware-level crash or a complete logic collapse in its internal ROM or RAM memory. When the BMS loses the ability to guarantee the accuracy of its own data or its software execution, it's flying blind. And let's be real, in a high-voltage system, a blind monitor is a terrifying thing. You're risking overcharging, massive current spikes, and extreme thermal runaway. So here's our roadmap for today. Our ISO 2626 compliance safety mission briefing, if you will. 1. The microscopic battery threat. 2. The triple safety net. 3. Designing for disaster. 4. Bulletproof manufacturing. And 5. Extreme stress testing. Okay, Section 1, the microscopic battery threat. We're looking at the unseen forces attacking the NCU. We have to start by looking at the environment, right? Because these unseen forces are constantly attacking the microcontroller unit, or MCU. And we aren't talking about big mechanical failures here. These are microscopic, silent threats, like literally cosmic rays. We're talking about single event upsets, or SUs. You see, an EV battery box is an incredibly noisy environment. You've got high voltage, high-frequency electromagnetic interference, or EMI, sometimes that high-frequency noise from the inverter, or actual high-energy neutrons from cosmic rays at high altitudes, pierce the protective casing and physically hit the silicon lattice of the microchip. When this cosmic bowling ball hits, it creates a tiny transient electric charge. And that tiny charge can alter the state of a memory capacitor, causing a single bit to instantly flip from a 0 to a 1. If that flip happens in a critical line of code, boom, the system deadlocks. And you know, it's not just cosmic rays. We also have to worry about something called a brownout. Imagine you turn off your car. The BMS needs a microsecond to save its critical historical data, like battery health and fault codes, to its memory. But if the 12-volt auxiliary battery is getting old, or say a heavy load like power steering kicks in at the wrong time, the voltage can suddenly dip below 4.5 volts. This sudden drop interrupts the flash memory right in the middle of writing. The result is corrupted data and a completely destroyed CRC32 checksum. So the next time you turn the car on, the system reads that corrupted data, fails its safety check, and throws that P0A0E fault come. On top of cosmic rays and brownouts, there's also just simple physical degradation. Extreme high heat, especially the kind you get during fast charging, accelerates this microscopic tunnel effect, where charge simply leaks out of the memory's floating gates. Plus, if the software is poorly designed and constantly writes highly dynamic variables, like the state of charge, into the memory millions of times, it literally wears out. It causes permanent physical destruction of the tiny silicon dioxide insulation layer, leaving you with permanent dead spots. Moving right along to Section 2, the triple safety net, the hardware and software architecture. So clearly, the microscopic world is incredibly hostile, but here is how engineers build the hardware and software architecture to catch these invisible errors and meet the highest automotive safety standards. First up is your software defense, the March-C algorithm. While your car is running, the BMS software is actually running secret, constant background checks on its own volatile memory. It uses this clever checkerboard pattern of zeros and ones, constantly writing, reversing, reading, and cross-checking the memory blocks. If it detects that a memory cell is stuck at a 0 or stuck at a 1, maybe from one of those cosmic ray strikes we talked about, it instantly catches it and flags a P0A0 fault code before any real damage can happen. But here's a question. What if the main processing brain itself makes a mistake? Well, the solution is lockstep dual-core processing. The microcontroller actually has two identical brains, Core A and Core B. Think of them like two accountants doing the exact same math. Core A executes a software instruction, Core B executes the exact same instruction, but just 1 or 2 clock cycles later. Then they instantly compare answers. If an EMI strike flipped a bit in Core A, Core B is going to have a different answer. They spot the lie instantly, use hardware error correction codes to fix single-bit errors on the fly, or they trigger a fatal erupt if the error is just too severe. Okay, but what if the entire dual-core chip dies completely? That brings us to an unbelievably small margin of error, 2 milliseconds. Outside the main chip, there's a totally independent component called a system basic chip, or SBC, and it runs a window watchdog. It's basically constantly asking the main processor for a heartbeat signal. If the main processor deadlocks and misses that strictly timed window, the SBC doesn't ask any questions. In under 2 milliseconds, it bypasses all the software and physically cuts the gate driver, safely shutting down the high-voltage system. 2 milliseconds to prevent a disaster.
Which brings us to Section 3, Designing for Disaster, DFMEA Severity 8 Interventions.
In the engineering world of design failure mode and effects analysis, or DFMEA, these memory lockups are rated a maximum severity of 8. You absolutely do not mess around with a severity 8. So the crucial part is how we engineer our way out of it. Remember that 12-volt brownout we discussed earlier? Well, to prevent memory corruption when the power suddenly dies, engineers design the circuit boards with massive low-resistance decoupling capacitors. These act like tiny backup generators that give you a 50-millisecond lifeline. And that 50 milliseconds is just enough time for the processor to safely finish writing its data, calculate its checksums, and shut down gracefully. It completely avoids a corrupted memory save. We also design a really cool self-healing mechanism into the flash memory, using dual bank flash partitions. Basically, we never just save data in one place. We use Bank A and Bank B. On top of that, we use wear leveling algorithms to spread out the data writing so no single sector gets worn down too fast. Now, if a brownout does happen and Bank A fails its checksum at startup, the system doesn't just die. It automatically unlocks the mirror backup in Bank B, restores the system, and literally heals itself.
All right, Section 4, Bulletproof Manufacturing, PFMEA Factory Controls.
You know, you can design the most perfect system in the world, but it means absolutely nothing if it's not built perfectly. And this is where process failure mode and effects analysis, or PFMEA, comes in. These are the relentless, almost militaristic factory controls meant to eliminate any manufacturing variation. There is zero tolerance here. Everything has to be 100%. Because static electricity can destroy the microscopic layers of a chip, there is 100% dynamic electrostatic discharge monitoring on the assembly line. That means every worker, every machine, every tool. And because you literally can't see the solder underneath a microchip, there is 100% 3D X-ray screening looking for microscopic cracks or voids that could cause a disconnection. During programming, there is a 100% data readback to verify the checksum is locked. And before any board even thinks about leaving the factory, it goes through full functional testing, including simulating heavy engine start voltage ripples just to ensure the power management is totally flawless.
Finally, Section 5, Extreme Stress Testing, the DVP&R Gauntlet. So before mass production ever begins, these physical units face a brutal gauntlet. This is the Design Verification Plan and Report, or DVP&R phase. We push these systems to their absolute breaking points to ensure they can survive 10 years and 300,000 kilometers out there on the road. Engineers will hook the system up to a simulator and manually inject a stuck bit into the RAM, literally mimicking a cosmic ray strike. The pass criteria? The system has to detect it in under 100 milliseconds and instantly lock into a safe state. They will intentionally kill the 12-volt power to simulate a brownout. The system must hold up for 50 milliseconds and 100% auto-recover from its B partition. They will freeze it to negative 40 degrees Celsius, bake it up to 85 degrees, and violently vibrate it to test those solder joints, allowing less than 15% microcracks. And lastly, they will intentionally deadlock the main processor, just to ensure that independent SBC watchdog forces a hard physical shutdown of the high-voltage system in less than 100 milliseconds. I want to leave you with this thought today. In a 300,000-kilometer journey, a single bit will eventually flip. The engineering miracle isn't preventing the flip, it's surviving it. Modern EV functional safety isn't just about hoping things don't go wrong. It's the absolute, mathematical guarantee that when the microscopic world attacks, the vehicle recognizes it, isolates it, and most importantly, keeps you safe. Thanks so much for exploring this explainer with us, and keep learning.